Yeah, thanks a lot for inviting me. Yeah, today I will talk about statistical breakthroughs and hopefully some novel perspectives on deep learning theory. I'm actually working on this topic already since 2017 when I started my PhD in Darmstadt. And yeah, since that, like I never stopped actually, because the hype remained, and so I was just following the path, and now we are here. And I talked with a colleague from NYU, Mateusz Telgaski, who is one of the big names in deep learning theory, and he told me already in 2021 when we met the first time. Okay, this I could show you in a bit, but he told me, yeah, Sophie, you should stop working on deep learning theory. The field is dead. No one wants to hear something about this, because the fact is that deep learning's breakthroughs were not driven by any mathematical understanding. They actually evolved despite the lack of it. And we had a lot of breakthroughs in the last couple of years. Now everyone uses ChatGPT. Before we had diffusion models that can generate images. So we had a lot of these breakthroughs. They were basically evolutions of past architectures and training tricks, but those were also developed without any mathematical understanding. And before I go to the next slide, so the work I'm presenting from my side is joint work with Johannes Schmidt-Hieber, who is the chair of the Twente group, and Insung, who is here today, and Yun Tong, who are both postdocs of Johannes. Okay, so where are we now? So the fact is also that deep learning theory is basically phenomenological in the sense that we first observe something from empirical observations, and then people jump on this topic, try to build a simplified model, and then understand in this simplified model why is the method doing this good job there. And if we now compare theoretical tractability to practical relevance, then we are now basically here. So we are still talking about very simple network structures that have no relevance for practical applications. So these are these feed-forward neural networks, and for training, for example, we are not even there. So we are still talking about linear models, or diagonal linear networks, something like that. And so what happened in the last 10 years is that now we have models that have a huge practical relevance. I mean, transformers, LLMs, they are impressive, but theoretical tractability is like super minor. It's basically not existing. And so the question is a bit, so why should we still do this? Because it's a bit hopeless. So we are here, they are there, and we have a bit of trend that we are going more and more in this direction. But now I'm citing the godfather of AI, Geoffrey Hinton, who won a Nobel Prize last year. He was one of the big names who developed a lot of these architecture, and he said that there's a 10 to 20% chance that AI will lead to a human extinction in the next 3 decades. So he's very, very negative. He just left Google because of that. I hope that he's not right, but there's also a center of AI safety in the US. Not sure what will happen with it now, but before they tried to really stop the practical research because they realized, okay, there is no foundation for it, so no one really understands why is it working like this, so we have no reliability, so it's pretty dangerous of applying these models, especially in like fields like medical diagnosis, things like that. So there is indeed a huge need that we need to understand these methods, and of course also the weaknesses, and math somehow helps us to model this, math and also computer science, and then at least analyze it in these simplified settings. And what is nice about this deep learning theory field is that we somehow have to work with different disciplines. So if we want to analyze networks, we also need to understand how the optimization works. So we have to connect with optimization people, numerical analysis, things like that. So there are a lot of overlapping applications here. And what is happening, if you're checking arXiv probably on a weekly basis, there are like thousands of articles talking about any like new models, anything related to deep learning, but it's pretty hard to keep track. It's also hard to understand the notations that other fields are using. So for these theoretical foundations, there's a hope that we find a common language to really see so what was already done and what can be done in the future. So where are the gaps? Yeah, and the last thing, that's probably why we're all here. Math is also fun, and there are a lot of open questions. So yeah, that's why I'm also working on that. Okay, And this is the Venn diagram. I have it already since a couple of years because it summarizes a bit the theoretical results that were derived so far. So we have basically three different areas where deep learning were analyzed. We have approximation theory, and these are results that are dating back to the 80s, 90s, with people analyzing how expressive is actually this function class and what kind of functions can be approximated well by the networks and how do they approximate smoothness classes, things like that. In generalization, we try to understand why does this method generalize so well to unknown new data. And optimization is basically analyzing the training routine, so gradient descent routine or any variance of that. And what is nice from a statistical point of view is that in the end, statistics enables to model theoretically a prediction problem. And this is basically what these methods are doing. So they're predicting images or classifying images, things like that. And if we would model this theoretically, the estimator that we're then analyzing is basically addressing all these three different areas. So we need to understand why is it, for example, approximating the regression function well, why is it generalizing, and what is happening in optimization. So why is it close to the best optimization we can use. We are not there yet, it's just there is the hope that this is possible. Okay. And before I'm now talking about my own results, I want to go a bit to the past and mention some of the big not big breakthroughs, but major contributions that are still used quite a lot in the nowadays results that we're showing. Okay, so if we go back to the 1980s, 1990s, then people were talking about so-called shallow neural networks, and that are networks with only one hidden layer, that you see here. So who saw networks before, just to know if we're all Okay. Okay. So what is happening? So we have an input, then we weight this input by this beta vector, shifted by a bias term, and then apply an activation function. And after we have this activation function, we get these inner neurons. This is basically the graphical corridor to it. And then we weight these neurons, and this is the output that we get. Okay, that's why we talk about the one hidden layer, because yeah, there are neurons in this image. Okay, so then the question is, how large is this function class? What kind of functions can we generate, and how do they approximate smooth different functions of different smoothness? And there was one property that was basically the first thing people tried to understand whether a network has this property, and this is the so-called universal approximation property, which states that the shallow network with a specific activation function has this property if they lie dense in a space of continuous functions in 0, 1 to the d. And the thing, what is possible here is that the amount of neurons that we have in the hidden layer can be scaled with the precision. So the smaller the precision, the more neurons we are allowed to take. So this is not fixed. Okay, and then the question is, so what kind of networks do fulfill this? And first of all, it's important to note that not every network has it. For example, if you think about a polynomial activation function of a fixed degree R, then we are basically taking a weighted sum of net or of polynomials with a fixed degree. So if you think about a continuous highly oscillating function, there's no hope of approximating this with this network class. Okay? Okay, so there are a lot of proofs in the literature how to show that. Some are rather abstract and some are also informative about a bit what kind of functions can be approximated. And yeah, the first step was to go back to the univariate setting, so dimension 1, and consider activation functions which are continuous and not a polynomial. And then one can show, okay, the corresponding shallow neural network that we then have has indeed this universal approximation problem. Okay, and one proof idea is to model with the shallow neural networks polynomials of different degrees. And once you can do this, you use Weierstrass approximation theorem, which shows, okay, polynomials are dense in the space of continuous functions, and then you also have it for shallow neural networks. Here, for this construction, you need that you have an infinitely often differentiable function, but then this is a proof by contradiction, which then also shows that it holds for continuous functions. Okay, so once we had it once they had it for the univariate setting, then the question is how can we go to higher dimensions. So the first step was already solved. And then the second step is a bit of a detour. We are considering so-called ridge functions. Ridge functions have a similar structure to a network, with the difference that these GJs can be different. So usually we have a fixed activation function, and here the GJs can be chosen differently for each of the components. And once one showed this, that these ridge functions are dense in the space of continuous functions, then we can use the result from before, because that are univariate functions, and then we also have it for the networks. And there are many, many other ideas. So there are ideas via Fourier transform, random transforms. It's just one way of proving it. Okay, and so that was in the 80s, 90s. So no one was really training these networks. It was more of theoretical interest. And then in 2012, there was the big breakthrough of deep learning. So there was this AlexNet, and which were classifying images with a precision that no one saw before. And suddenly everyone was jumping on deep neural networks. What is now the difference to shallow networks? We not only have one hidden layer, but we have several. I denote the number of layers here with an L, and then we also have the width of the neurons in each layer, which is defined by this width vector. So it's telling us how many neurons do we have in each of these layers. So basically, we're taking an input, we're weighting it, we apply an activation function, and then we do this L time. Okay? And then we have a lot of these weight matrices and also some shift terms that are here in this V1. It's a bit of sloppy notation. And these weight vectors are in the end the ones that are trained with the given data. And then again, the question is how expressive is this function class? Here we are now not talking about continuous activation function, we are fixing really a network activation function, which is the so-called rectifier linear unit, which is just extracting the input, or it's set to 0 if it's a negative input. There's an x missing, so sigma of x. Okay, so then the question is what can we do? And it's a super easy idea, but it was used quite a lot in approximation theory, and this is a result by Matouche, who showed that the truth function, that is a function that looks exactly like the one in the upper right corner, that if we compose this truth function and then weight it and add it up and subtract our input, then this function approximates x squared on interval 0, 1 with this precision that depends on the compositions that we consider. And it basically looks like this. Okay, so the higher the amount of compositions, the closer we get to the curve, and the better we are with approximation. Okay, so why is that now interesting? Because these functions look already a bit like a ReLU network. So a ReLU network is 0 and then something linear. So if you're adding up piecewise linear functions, you can, with error 0, represent it in this way. Okay? So then we already had it for also the networks of layer with the amount of layers R. And why is that now cool? Because once we have it for x squared, we also have an approximation for multiplication by using polarization equality. And if we have it for multiplication, then we can do this component-wise and then get approximation for a product of the components. If we have this, then we get monomials. If we have monomials, then we can do polynomials. And then we are close to like any smoothness class that has a nice Taylor expansion, so Hurley smooth functions of a left space is something like that. So the idea really goes back to x squared, and everything else is feels a bit like playing Lego or something like that. So you're setting together different bricks. You always have to take care of the errors that you make during approximating this, but the idea is pretty simple. The second result, which had a huge impact, was a result by Peter Bartlett and co-authors, which were analyzing the complexity of network classes. I'm not defining the Wapnick-Chernyshevsky dimension here. It's a way of measuring the complexity of a function class. And what they showed us that if you take now a network class which has L many hidden layers, and are neurons per layer, then the complexity also only depends on the size of the network. Okay, so this point here. Okay, why is that now interesting for deriving statistical risk bounds? Because if you want to bound the risk, it's now also again very sloppy notation, of a neural network, for example, an L2 risk, something like that, then you can decompose this term in exactly the three parts that I showed you in this Venn diagram before. So you have a term which checks, okay, if this is, for example, an empirical risk minimizer, then you're here checking, okay, how close is the network that we trained to this empirical risk minimizer. I have one term where the question is, how good does it approximate the function that I want to learn? And I have this generalization term. And the generalization term is basically bounded by something which depends on this BC dimension. So we have this, and we have this with the result I showed you. And we ignore this, because we talk about empirical risk minimizer, so this guy is 0. Okay? So the articles that you see now here, and it includes now my own work during my PhD, they are all based on this idea. So they do this decomposition, then they have these two terms. The approximation is then changing because the assumptions on the regression function are changing, and yeah, then there are different network structures considered, but in general, this was the main idea of deriving these results. Okay, and I don't want to criticize this because I would also criticize my own work, but of course, it's coming with restrictions, and one is that all these results focus on a non-parametric regression setting. Then they are talking about these very simple feed-forward neural networks. And okay, this is a big thing. They assume an empirical risk minimizer and completely exclude the optimization. Okay. Why are now these restrictions problematic? So first of all, if you think about nowadays network structures, they are, I mean, transformers, it's crazy to write them down. The notation is super heavy. So the network structure and also the statistical settings are quite different to what can be described with the regression setting at feed-forward neural networks. And the loss landscape of networks is a highly non-convex loss landscape, so it's pretty unclear where we will end with our gradient descent routine. So the question of analyzing the empirical risk minimizer instead, maybe it's not really informative to what is really happening. Okay? This is super hard to do. So this is the part where people are not talking about deep networks still. So they really have this very simple structures and try to see what is happening in these training routines. So today I want to talk a bit about this part. Okay, and we go back to the setting that all these articles had in common. So this is the non-parametric regression setting. So what is it? Basically, it's a signal plus noise model. We have a label y. We have a function f, which describes the relation between my input and my output, up to some measurement noise. Okay. And if I now want to know how good is this estimator, then okay, I'm taking the square distance to my two labels y, and then I can decompose this term decompose this error in two terms. One considers, okay, how good is my estimator compared to the regression function, and another one is not controllable by us because it's the noise that we have in our data. Okay? So if we now translate this to images, then what can happen is, okay, I can be very good in this term, but there is potentially very high noise in these data, so this guy will dominate the whole error. It's not really giving us any information why are these methods now performing so well on images. Okay, so what would need to happen is that the variance goes to 0 also with a higher sample size and quickly enough. Okay, so that was a bit the motivation when we started the project. It's already a few years ago, we're still working on it. So we said, okay, let's do image classification and let's think about another model that we can analyze instead. So what is an image? An image is first of all nothing more than a matrix of pixels, which tells us how high is the intensity at a specific spatial location. And if you read a bit the literature, then people used to say, okay, image classification is a very high dimensional classification setting. Each pixel is an independent variable. And if I'm now learning this functional relation between input and output, it's getting considerably harder if I have more pixels. which means if the resolution of this image is higher, the performance theoretically goes down. But this is a bit in a contradiction to what we see in practice, because, or also if you think about yourself, detecting highly resoluted images is way easier than ones that are very pixelated. So we thought, what could we do instead? And we said, okay, actually, an image is a highly structured object. So instead of considering each pixel as a random variable, we now define a template function, which I denote by f. And each pixel is just an evaluation when we integrate over each of these small pixels. This is a rectangle which denotes one of the pixels, so we're integrating the function over this small rectangle. Okay? So that means now, if I'm increasing the number of pixels here, then I get more evaluation points of my unknown function, and so I would expect a better performance if I'm giving more information about this unknown template. The second thing is that different images often come because of different geometric deformations. So I think standard deformations is scaling, shifts, rotations. Of course, there are many, many more. Also in medical image registration, there are many ideas of describing deformations. But if you think about very simple ones, then rotation, scales, and shifts are probably the easiest. Okay, so if we take both together, we are able to build this simplified deformation model. So first of all, this is my original image, so I'm using this model now. And now I'm applying 3 different deformations. So I have a scaling factor, which is my sine psi prime. And if I'm now increasing this, then I get a shrinked image. And if I'm decreasing it, I get a scaled image, which is bigger, either stretched or shrinked on the x and y axis. Okay. Then I have these factors tau and tau prime, and they describe shifts, so like moving left, right, up, down. And I have a brightening factor, so if I'm multiplying this with a higher value, I get lighter pixel and vice versa. Okay, and yeah, we had this, we liked our model, we submitted it to JMLH, and there was like, yeah, nice idea, but way too simple, no one cares. So we were like, that's why this project is so old now, because then we tried, can we come up with something more general? And that's the best we could do now. So instead of fixing our deformations, we now take an invertible mapping A, which is now also able to describe other deformations. For example, a general matrix. So you can include your rotations, you can include different other deformations here. By functions, which are depending on the position of the pixel. And if we do this, we can describe local deformations. This is an idea of Stefan Mallar. He did this in the early 2000s already. Okay, and because we are statisticians, we of course wanted to do some prediction. So we took again the easiest you can think of, binary image classification. So we have images, corresponding labels, and we either have label 1 or 0, so distinguishing between cats and dogs, something like that. So we have exactly the model that we saw before, with the difference that, of course, for different image classes, we have different template functions. Okay, so F0 or F1. So what is unobserved? Our AI, which are random vectors / matrices that are drawn from a set of deformations A. And we need some assumption, and the first one is that I have 0 background, so blank background, so every signal that I detect, so every pixel which is larger than 0 really belongs to the object I want to classify. And I need that the object is fully visible. So there's no way of moving it halfly out of the image, something like that. So what does it mean from a mathematical point of view? We need assumptions on the support of our template functions, but of course also on the deformations, because if you think about an image which has a huge scale, then there are not many options of moving it out, of shifting it without moving it out of the image. Okay. Okay. So if I'm now comparing a bit what is the goal of a regression setting and what is the goal in this model. So regression setting is basically a denoising problem. So we want to do some local smoothing. And in our model, we are in the end having these deformations, but they are completely uninformative to classification. So we want to come up with a method which is invariant to these potential deformations that can arise. Okay, And we came up with two approaches. I only want to talk about the second one, because the first one was more a benchmark approach. So we have a method which is perfectly aligned to possible deformations. If we fix the deformation class, so we know the deformation class, then we can come up with a model which perfectly classifies the labels. And also, so it's a bit about what is the best we can do. And the second one is because we work in deep learning theory, we want to use a network, and the default choice for images are convolutional neural networks. And so the question is how is this CNN now solving this task? Okay, so what is a CNN? The main component of a convolutional neural network is the convolution. So what is happening is we have an image, and then we define a small weight matrix, which is this purple square, which has some fixed entries. And this matrix, this filter is now moving over the image, and at each position where it stops, it's computing pointwise the pixels that are mapped by the filter. So it's a product, it's a sum of a Hadamard product in the end. It's adding them up and putting them as one entry in this feature matrix that I get in the second layer. Okay? And this sliding of this filter, we do not only have one filter, but we have several. And if we do this sliding with several filters, we also get several feature maps. And what is usually followed by a convolutional layer is a so-called pooling layer. What is happening in this pooling layer is basically helping us to decrease the dimension. For example, it's extracting the maximal value at some smaller spatial position. Okay? And after this, a fully connected layer is attached in the end. Okay? So what was a bit the motivation of building such a structure? The idea was to say, okay, probably by having these fixed filter matrices, the method learns high-level features. So for example, first detecting ears, first detecting eyes, and then combining these different features for, like in a hierarchy, and giving information about the final object that we had on it. So that was the motivation of having this structure. That was actually Geoffrey Hinton who came up with this network structure. Okay, so we took exactly this network, but we simplified it even more. So we said we only have one convolutional layer, not several. We again have a rectifier linear unit as an activation function. And in this convolution that I just described, we're not having one filter, but we have k many. Okay, so we do k, we have k times the sliding over the image. Okay, so we get k many feature maps in the end. I describe this convolution for now with this star. Okay. I apply pointwise my activation function, and then I do a pooling layer, and we are doing the global max pooling, so we are just extracting the maximal value of each of these feature maps. Okay? So we have k filters, we generate k feature maps, and we extract the maximal value, so we're ending up with a k-dimensional vector. And this vector now goes in a feed-forward neural network. That's exactly the definition I showed you before. With the difference that in this last layer, we now need something which lies between 0 and 1, because we want to do classification, so we want to see what is the probability that the image belongs to one class or the other. Okay? And again, these matrices is something which is usually learned by some training routine. Okay, so what is our final architecture that we're considering? So we are for now fixing a natural number m. So we need 2m convolutional filters, so that are the amount of filters that are sliding over this image. We do this global max pooling, so extracting the maximal value from each of these feature maps. And then we have a logarithmic depth of fully connected layers before we get a binary output, which tells us what is the probability of having a cat or a dog or whatever classes we consider. Okay, so why is this architecture now better than a standard feed-forward neural networks? Because by just built-in architecture, it already has some invariances. For example, it is nearly invariant to shifts. So this network has a fixed filter which slides over the whole image. So it's generating these feature maps And the position of the signal in this feature map is in the end not important because we're anyways just extracting the maximal value, so we don't care if the signal was in the upper left or the lower right corner or something like that. And then there's the question, is it also good to have some inbuilt architecture which is scale invariant or rotation invariant? And there are debates in the literature about having filters that are invariant to group actions, so-called group CNNs. But if you take a natural CNN, they are not having this property. Okay, so they are not scale invariant. So we have to come up with something which is also taking different scales into account. Okay, so we want to do classification. We have a supervised learning framework, images, and corresponding labels. The first step we do is we normalize the pixel values, and we get invariant to the brightness that we had in the beginning. And we again doing an ERM, so we just say we take the estimator which minimizes this 0-1 loss. Okay, so we are just counting the misclassified labels, and we want to keep this misclassification as small as possible. Okay, this is NP hard. So if you train this, no chance. So usually you would do a surrogate loss instead, some cross entropy loss. It's a bit to the report. We now have it also for cross entropy loss, so it's possible. But I think it's nice to think about, okay, we just count our classifications here. Okay, so what is the final class label that this estimator assigns? It's a plug-in classifier. So if my probability that the label belongs to one class is higher than 1/2, then we give the label 1 to this, and otherwise 0. Okay, so what can we do? We assume the object is fully visible, so this means we have some assumptions on the support of the template functions and also on the possible deformations. And we have a parameter m, which is later defining the network architecture, and this is some covering number over the deformation class. What does it mean? So I'm considering balls with a distance radius of 1/d that is covering this class. And if you think about a class where we have scales, where we have scales in brightness, then this is a d to the where we only have scales, then you have a d to the 2. If you have also rotations, you get a d to the 3 because you have another angle for the rotations. Okay, then this is a strong assumption. We need that the template functions are Lipschitz, so no sharp edges. But this is something which makes our theory way easier. And we need a separation criterion, which means if we have two template functions, then it shouldn't be possible that one template function describes or that the deformation of one template function is the same as the deformation of the other template function. Because if this is possible, then the pixel, it's not clear to which class the pixel belongs. So we need these two deformed template functions to align at least with a distance of 1 over square root of d in part. Okay, so we have this plug-in estimator which is minimizing the misclassification error. And then the probability that we are misclassifying can be bounded by this term here. So we have some logarithmic terms that we're a bit ignoring. And then we have some rate 1 over n and some md to the squared. If you think about a scaling class, you get a d to the 4. If you think also about rotations, you get a d to the 6. So if you compare this a bit to a regression setting, then usually you have these rates of n for smoothness classes n to the minus 2p over 2p plus d. So d is usually in the exponent, and if you increase d, then this gets very, very slow. Still, we need to have a trade-off between sample size and dimension, but it's way more favorable than what we have in regression. So we are not really affected by the curse of dimension. Okay, so what is some remarks on this rate? Okay, nice, it's converging to 0. Then it's a rate, but we don't have a lower bound for it, so we are pretty likely that this can be improved. We haven't shown it yet. I don't know how hard it is to show, so we are thinking about this right now. Again, this approach that I showed you before in having a complexity term and the approximation term is the same approach. So one part, this complexity term is already done with the VC dimension part I showed you, and the hard part is now the approximation theory around it. So how do these convolutional layers really learn these invariances of the deformations? And the fully connected layers are in the end extracting a maximal value. So this is what the approximation result we had here for these fully connected. And one thing we haven't solved yet, but what is interesting to do probably is to use this deformation model to generate new data. So one could start with some real images, and because maybe real images are costly, for example, in the medical field, then one could probably use this deformation model, generate synthetic data, and go with this synthetic data in the learning process. The problem is that if I'm starting with a real-world image and then apply deformations, I'm running into a dependent data setting. So this approach of decomposing is heavily relying on an IID set. So it's a bit the question how to start. So how can we bound this? So either we are able to just say, okay, the dependency is rather small, so we just have this as an additional term and carrying it through the analysis, or we need another way of bounding this. Okay, so then a bit about this separation criterion. So what we could show is that if we have a separation which starts with being 1 over d apart from each other, then one can show that the pixels can be either represented by one of the template functions or the other. And if this is possible, of course, then it can belong to one class or the other. So indeed, we need a separation. The separation that we have in this result is not optimal. So we could be better. So we could do it for 1 over d. Again, it's more technical work. So we said, okay, for this CNN structure, we live with the fact that it's not matching the lower bound directions. Okay, so a bit the comparison of a non-parametric regression setting and our image deformation model. So what are we doing in non-parametric regression? We're doing denoising, local averaging. In our model, we do invariance of labels. We learn these invariances under deformations. In this non-parametric regression setting, we have a feed-forward neural network. We are now at least using a CNN structure. Still, this is far from the state of the art. So even for images, now transformers are used. We are able to avoid this curse of dimensionality. We can be in an overparameterized setting, which is in the non-parametric regression setting solved with sparsity. And this model has 0 training error, so we really have that it's perfectly learning these labels, and even we still have a good performance on new data. This is something which is cannot be shown in this non-parametric regression setting. And okay, this is my conjecture. The data augmentation is here not possible, and here it is. It's not proven, so it's a conjecture. So this image deformation model is of course very limited. So I need, for example, that the object needs to be fully visible. I have 0 background. So there are a lot of ideas how can we deal with halfly moved out images. What other deformations could we consider? So it's the starting point of probably analyzing this problem from a different angle. Okay, that was a bit the motivation of this project. Okay. So the question is then what's next? So what should we do? And I think, do I have the time for talking about this? Or I can mention later. So I will talk a bit about networks with Heaviside activation functions. So if when I mentioned the literature in the past, I didn't went back to the roots. So the first thing that was done was the so-called perceptron by Rosenblatt already in the 50s or 40s, something like that. And it was a first approach of modeling neural activity. So it was a single neuron that you have here, and the single neuron gets some signal, some input from previous neuron, and then it's firing yes or no. That was the idea. Okay. And then there was an algorithm implemented that were able to learn this, and then people realized, okay, but there are a lot of problems, very simple classification problems that this algorithm can't learn, so no one was interested after 10 years or something like that. So people started in the 50s with Heaviside networks, then these smooth functions were used instead, like going from one neuron to one hidden layer network because it has more expressivity. Then we had these ReLU networks, and now I learned also from Matouche that no one uses ReLU anymore. I wasn't aware of this, but now there are new activation functions, which is called GLU. So there is some Gaussian noise applied on it to smooth out this one point here, and there are more. So it's and the question is, so what should we now do with this? So should we just follow all these practitioners that are coming up with new activation functions every year and then try to do theory for this? Or, and that's what we did with Insung. Insung was actually the person who did most of the work, go back to the Heaviside activation function. Okay, and this is what we did, because in 20 we talked a lot about biological inspired learning. Now people are talking about spiking neural networks, which are neurons that are time dependent and firing after a specific time point. But if you take the simplest structure, the activation function is an all or none firing, so it's saying yes, no, so 1, 0. Okay. Then now I had one Nobel Prize winner on the Geoffrey Hinton, the second one was John Hopfield, who invented these Hopfield networks. And the Hopfield networks also have the Heaviside activation function. And nowadays we're talking about, a lot about energy efficient AI, because training these transformers is computational super heavy. I just learned that all these different companies, they invent a better model, then everyone uses their model, and then they're decreasing the performance because it's so expensive, so then they're just happy everyone uses them, so they go back to an earlier version because this is cheaper. Okay, so why Heaviside networks? Because they are basically extracting bits, so the memory is lower than for other activation functions. Okay, so what was our architecture? In the end, it's the same structure as I showed you before. So we have two parameters. We have the depth and the number of neurons in the hidden layers. So this is a graphical way of representing it, or we can also use the same notation that I showed you before, with the difference that this is now a Heaviside activation. Okay? And by this DHN, I'm now just denoting the whole class of functions that have exactly this form. Okay? Okay. So expressive power of Heaviside network. So what is it doing? So we have one neuron which has this form. And now if we're adding up these neurons, we're ending up with a piecewise constant function, which looks like this. Okay? So the question is, so how good does it actually do? Does it in the end approximate continuous functions? And here we can derive a lower bound, and this lower bound in the end only depends on what is happening in the very first hidden layer. Okay? So we have an input, and after the first hidden layer, we are losing all information except of some intervals which are telling us, is my x lying in this interval, yes or no. So we're ending up with a piece, with something like this. Okay, so depth is not giving us more information because this lower bound is not caring about the neurons in the later layers. And the proof is pretty simple. So just for notations, we define now our function on the segment between x1 and x2. That's what we read in the proof. And okay, what one can show is that if f is a piecewise constant function which has at most k1 plus 1 pieces, then this is what the Heaviside network is extracting after one hidden layer. What we can further show is that each output of neurons that we have in some specific layer is again only a piecewise linear function, where the number of pieces depends on the neurons that we had in the layer before. Okay? But this means that if we have two inputs that lie in the same piece, then they have also the same value here. So this means if we want to derive the lower bound for this guy, we can also just check how good is the piecewise constant function approximating it. And okay, then we get for continuous function exactly this 1 over k1 plus 1 bound here. Okay? Because we're basically doing this in here. Okay. And then we also checked a bit what is the tightness of the bound, and one can show that we get the same upper bound if we take a specific structure of a function, either a ridge function of this form or some Lipschitz function, then the upper and lower bound are matching. So yeah, it's tight. Okay, so then the question was a bit, okay, now we learn from this result, depth is not helping. Usually we always wanted to talk about deep networks, but there are indeed advantages of having more layers. One example is that we are able to approximate x on a hypercube, or also this x4 function that you have here can be represented by a Heaviside network with 2 layers, but not with 1. Okay, so there are examples of functions that can only be represented by a deeper structure. Okay, so we wanted to improve the expressivity. So we said, okay, what we lose after 1 layer is the information of the input. So we avoid losing this if we have skip connections. So in every layer, we are now giving this information in this layer. So we still are able to use my input x. Okay? And this is my function class with the skip here, the same as before, with the amount of skip connections that I have in each layer. Okay, and if I'm now checking the lower bound, then I see that this bound is now heavily depending on the number of skip connections that I have. Okay, so this is now the amount of neurons that get the input in this layer. And even if you have only 1 skip connection in each layer, we see that depth helps because then we have a 2 to the L here, and this is going to quickly to 0 if my L is large. Okay. So okay, we were somehow hopeful that depth is indeed makes sense here. So we thought about, okay, we want to do approximation theory for these deep Heaviside networks. So we follow the same approach as I showed you before. We want to start with x squared. But if you think about this sawtooth function I showed you before, then there's no way of approximating this with the deep Heaviside network. So here we need to come up with a fundamental new step. Okay? And this is what we could show, and I think now I'm running out of time. But we can indeed show that by some bit extraction idea, we are in the end able to approximate my x squared, and I see again an improvement of with the number of skip connections that I have, so with the information I'm giving to the next layers, and this is up to the factor 2 that we had, matching also my upper bound, my lower bound. Okay, to wrap up a bit, so if I'm comparing this now with the performance of a ReLU network, then one would see that we need way less parameters to do the same thing. Okay, so we do some bit extraction, so we need a very high amount of neurons in the end to extract bits, to check if the values lie in some specific interval. So we use that we can represent x by some radix numerical system and then detect the different values there. But as I said in the beginning, of course, the memory is lower if we have these individual bits. So it's a bit up to you whether you think it's a nice thing to analyze, yes or no, because ReLU networks, if we just count parameters, are way better here. Okay, yeah, we have more results. I don't have time for that. So just to wrap up, so what comes next? So what we now did is we built some theory around Heaviside networks. So this goes in the direction of analyzing biological inspired learning. So in Twente we have this group of working on exactly this, and there are other people that are now also focusing on spiking neural networks, and it's also zero order optimization where you do not have information about the gradient of the function. But of course there's a lot of literature on large language models now, and I attended a workshop in Maryland in November, and I realized that a lot of the people that did theory earlier are now more analyzing the pure algorithms. So they had results like, what is the logical thinking of the LLM for a specific math task, and if they know this method is hallucinating, where's the logical thinking not working anymore? So it's more analyzing the pure algorithm. And so the question remains, what is the purpose of theory? So is it just fine staying phenomenological? I think there's no hope of catching up right now. But yeah, that is something I said in the beginning, and to me it's very important. There's a high need of exchanging fields of talking to people from approximation theory, optimization, numerical analysis, and so on, and really have this openness of learning from each other, or probably building even joint projects. Okay, that's it. Thank you.